Hello, welcome to The Naked Scientists, with me, Chris Smith, and also with Kat Arney.
Hello, and this week we're looking at making better batteries to find out if scientists can help your phone download just one more app before it dies. Plus, in the news, switching off paralysis from spinal cord injury and the chances of finding life on Saturn's icy moons.
The Naked Scientists podcast is powered by ukfast.co.uk.
Now, before we kick off with the news, a quick quiz question for you. Can you tell us what voltage do you normally get out of what we call an AA battery? If you think you know the answer, email chris@thenakedscientists.com or tweet @nakedscientists. News time now, and this week scientists have found a way to trigger nerve cells in the spinal cord to regrow when they're damaged. Ultimately, this might help patients who have been paralysed by spinal injuries to regain some control over their bodies. Neuroscientist Simone Di Giovanni from Imperial College in London has been leading the work, and he's with us. Hello.
Hello.
First of all, why is it such a problem when people injure their brain or spinal cord? Why doesn't it naturally regenerate?
Well, following spinal cord or brain injury, nerves do not regenerate, and this leads to disability, which can be really very, very severe and long-lasting, potentially forever.
But when someone injures, say, their fingers or their arm, if someone has a horrible accident and has a body part reattached, they do regain sensation or movement in those parts, don't they?
That is right. There's a striking difference between the capacity of the limbs, for example, to regenerate the nerves, and the spinal cord or the brain. And we are just now beginning to understand the fundamental reasons for this striking difference. And what we did is to contribute to this understanding by identifying a way where we can switch on the regenerative potential in the spinal cord and in the brain by learning how the limbs, for example, are able to switch on their regenerative potential.
Why do you think that the brain and spinal cord don't regenerate naturally, given that things like arms and legs can reconnect nerve cells if they're damaged? Why is that process purposefully disabled in the central nervous system?
Yeah, well, this is a very interesting question that I get asked quite often, and I do think that the main reason is because in our limbs, in our hands, for example, the anatomical structure is so much more simple than what we have in the spinal cord and in the brain, that regeneration and regrowth can be successful, while it's actually known that partial regeneration and regrowth in the spinal cord in the brain can lead to side effects, like pain, for example. So maybe the system is not ready to do it by itself, and we have to find a good way to help it out.
So talk us through the study in a bit more detail. What genes turn on or off when nerve cells are injured, and how does this alter or compare between nerves in your arms and legs and your spinal cord, for example?
There's a group of genes, so-called regeneration-associated genes, which are turned on in the periphery, let's say in the limbs, and they're not turned on in the spinal cord. And what we have identified is a so-called epigenetic key factor called PCAF, which is responsible to switch on a number of these genes all together. And this is something quite special, because with the one shot of gene therapy, if you allow me to say that, we can now switch on several genes which promote regrowth of nerve cells instead of having to do it one by one.
Again, you've got this molecule, this PCAF molecule, which can trigger nerve cells to want to regenerate, if I'm allowed to say want. But the point is, what makes that PCAF turn on in a nerve in your arm or your leg, but not in the spinal cord?
Yeah, there are specific signals which are transmitted from a cut nerve, for example, in a leg. And these signals are so-called phosphorylation cascades. They're chemical signals that tell PCAF to be turned on to promote the regeneration program. These specific biochemical signals are silent within the spinal cord.
And you have used gene therapy to put those signals into the spinal cord, and when you do that, the nerve cells there behave as though they're in an arm or a leg, and they try and regrow when they're injured.
It's almost correct. Let's say there are the signals that activate this gene called PCAF, and then which in turn activates the regeneration program. We, by gene therapy, delivered PCAF, which is in the middle between the signaling, and we activated this gene, and now we triggered a regeneration program. Yeah.
And when you do this, what sort of level of regeneration or repair can you get in the brain and spinal cord? Is it a clinically relevant amount? If you're an injured person who is currently paralysed by their injury, would the amount of repair or regeneration you're getting in your studies in animals actually produce a meaningful benefit to that person?
Well, this is, of course, I would say it's an impossible question to answer. So in principle, the answer is yes, but we have to perform, and we're planning to perform, specific studies to address whether this level of regeneration enhances recovery following spinal cord injury in mice. And after we've done that, we can translate that into humans, in patients.
Simone, thank you very much. That's Simone Di Giovanni, who is from Imperial College in London, and he published that study in the last week or so in Nature Communications. Kat.
Thanks, Chris. Now, Wednesday, April the 2nd was World Autism Awareness Day. But what is this often misunderstood condition? Here's your Quickfire Science with Hannah Critchlow and Kate Lamble.
Autism was first described as a unique syndrome in 1943 by the American psychiatrist and physician Leo Kanner.
Today, autism spectrum disorder, or ASD, is recognised to affect around 1 in every 100 people worldwide.
Every case is different, but everyone on the spectrum shares 3 main areas of difficulty: social interaction, communication, and imagination or flexible thinking.
On the flip side, people with ASD may exhibit common strengths with focused attention to detail, an excellent memory, and a tendency to logical thinking.
Other common traits of ASD include a love of routines, sensory sensitivity in one of the 5 senses, and having intense special interests, topics that they enjoy talking about and engaging in over and over again.
However, it's hard to characterise a condition which ranges from the 1 in 10 people who cannot speak to those who are high functioning and have a milder form of autism spectrum disorder.
ASD symptoms typically start to develop in early childhood, but some people with milder forms are not diagnosed with the condition until adulthood.
In the past, some people believed that the vaccine for measles, mumps and rubella caused ASD. However, further investigation showed that there is no link between the two. Instead, the age at which communication problems begin to appear in ASD patients is around the same age that the vaccine is given.
While we don't yet know the cause of autism, it's been suggested that high levels of testosterone in the womb may affect brain development and lead to the condition. This might be why males are more likely to have autism than females, at a ratio of about 4:1.
Genetics also seems to play a role in 90% of autism cases, with an increased risk of a baby developing the disorder if relatives have it. But it's likely that many genes are involved, possibly interacting with environmental factors.
There is no cure for ASD, but education and behavioural support can help. If you're concerned that your child may exhibit characteristics of the disorder, visit your GP, who can refer you for an assessment.
That's Kate Lamble and Hannah Critchlow, and you can get hold of all our Quickfire Science episodes as their own podcasts from our website at nakedscientist.com/quickfirescience.
You're listening to The Naked Scientists with Kat Arney and also with me, Chris Smith. To outer space now, and Enceladus, one of Saturn's 62 moons. This one's important because it gives rise to what some people have dubbed the biggest geyser in the galaxy. Not a big bloke, it's actually a periodic plume of salty water which jets thousands of kilometres out into space and even contributes to Saturn's ring system. Now scientists think that they've pinpointed where this water is coming from. They think they've got evidence for a giant internal ocean which is deep within the moon. And Madhu Sudan is a lecturer at the Institute of Astronomy in Cambridge, and he's with us to tell us a bit more about it.
This is actually a very exciting discovery. The Cassini mission, which has been close to Saturn for more than a decade now, has made several flybys across the moon Enceladus, and as early as 2005, which was just a year after it's going into Saturn's orbit, it found these plumes coming out of the southern pole of the moon Enceladus. So there were theories saying that there should be an ocean beneath its icy crust, which should be the source of this water vapor and salts that are coming out of these vents in the southern side.
What's
Now,
powering that phenomenon, though? Because to jet water thousands of kilometres into space takes a lot of energy. So where's that energy coming from?
Recently, in the past four or so years, there have been recent studies suggesting that it's the tides caused by the planet Saturn itself and another moon in the system. The tidal energy is causing these vents to squeeze and open up as the moon is going around the planet.
So it gets a gravitational massage, for want of a better phrase, by Saturn.
Exactly.
And this causes friction to heat up the water.
Mm-hmm.
So the water must be coming from somewhere. Is this just ice melting? Or do we think there actually is a big reservoir of water inside Enceladus?
So that's where the latest study comes in, which basically points to the possibility that there's a big ocean in the southern side of the moon that lies 30 to 40 kilometers beneath the icy crust. And the water itself, the water layer itself is estimated to be about 10 kilometers in thickness.
Gosh, that's a pretty deep ocean, isn't it? I mean, that's on par with the deepest parts of Earth's ocean, isn't it?
Yeah, exactly.
In a moon which is only about, 500 kilometres across? It's tiny, isn't it?
In diameter. It's very small.
How did they use Cassini to work out what's going on inside a moon to the depth of 30 or 40 kilometres where you can't see?
Yeah, so the principle is actually very simple. They used Doppler effect. Basically, they were tracking the velocities of the spacecraft as it is flying by the moon. What happens is that the gravity caused by the moon itself alters the motion of the spacecraft across close to it. Now, just due to the force of gravity, there will be some subtle variations in the velocities of the spacecraft, and the ground stations can track the signals from Cassini at precisions below 0.1 millimeters per second, very, very precisely.
Good grief. And this probe is how far away from Earth?
This is about 1.4 billion kilometers away.
It's extraordinary, isn't it?
It is.
Basically, by looking at how the gravitational field of the moon influences the flight of the spacecraft, you can work out what must be inside the moon, but just how much mass must be there.
Right, the mass and the structure of the mass. So a camera on board the spacecraft itself has found a depression on the surface of the moon itself. So based on that, you can estimate what the gravity field should be. But they found that based on this Doppler effect, that they found there should be an additional source of gravity beyond what is inferred just from photographs, basically.
So they don't know it's water, but putting all of the data together, the gravitational measurements, the fact there's water issuing periodically from these vents in the South Pole, it only really fits with water.
It's not necessarily the vents itself, it's that you need an extra source of gravity to explain the Doppler measurements. And that has to come from a higher density than ice itself, and water fits the bill almost exactly.
And if you have got a source of water in this place, and it's clearly warm water, if it's expanding and blowing out into space like this, could that be potentially a home for something to live?
So water is a very good candidate for astrobiology. So yes, that's why this moon is very interesting. So the answer is yes.
A home from home, perhaps. Thank you very much, Madhu Sudan from the Institute of Astronomy in Cambridge. Kat.
Well, back here on Earth now, and UK scientists have shown that fathers who start smoking before puberty produce sons that are more likely to be overweight. Very confusing, sounds like it. Bristol researcher Marcus Pembry led the study, and he joins us now to explain more. What are you trying to find out that led to this study?
Well, we're basically interested in the possibility that some of our inheritance might go beyond the genome and be rooted in early life parental and ancestral experience, a sort of transgenerational response system.
So things that your parents do or your grandparents did are reflected in your own self then?
That's true. And that we were able to ask some questions along these lines in the Children of the 90s study in Bristol. This is the world's most comprehensive follow-up in terms of detail of 14,000 children and their mothers who were born in 91, 92. They were ascertained in pregnancy, and of course they're now 22, 23. And in all that time, we've collected an enormous amount of information, genetics, measurements, diet, everything else.
So tell me a bit about this particular link with smoking. So who were you looking at,
Well,
and what did you find?
What we were trying to do was to test a hypothesis that was generated by some earlier Swedish studies that showed that period before puberty, mid-childhood, was an exposure-sensitive period with respect to these transgenerational effects down the male line through the father. So what we were doing was we got information on when the fathers, and the mothers actually, started smoking. And although we had about 10,000 fathers responded, half of them had smoked at some time, 3%, 166, had started before the age of 11. So those are the ones we were interested in their offspring.
So then what did you find about the offspring of those particular dads?
Well, we analyzed the boys and girls separately, and we found that the sons, by the time they were in their teenage years, from 13 to 17, had much larger BMI than the comparison group. And the comparison group were all the others, the sons of fathers who had started smoking after the age of 11, and also the sons of fathers who didn't smoke at all.
This does sound quite strange. What do you think's actually going on? Do you think that there's something else happening that's influencing this, or is it some kind of effect of the chemicals in the cigarette smoke at that crucial time?
There are about 2,000 chemicals in cigarette smoke, so we don't know, but we know it has a big biological effect, smoking, and it seems that something is being transmitted through the reproductive system. You know, the exposure before puberty gets under the skin in some way. It endures. It affects the reproductive system, probably carried by sperm to the son, but could be, through the seminal fluid. We just, in humans, we don't know what the mechanism is.
Thanks very much. That's Marcus Pembury, whose research is published in the European Journal of Human Genetics this week.
Thank you, Kat. Well, crunch time now for cereals, because scientists have discovered that when the characters portrayed on cereal boxes make eye contact with you, people are much more likely to buy the product. And while adult-focused cereals tend to show the characters looking straight ahead, the more sugar-rich cereals, which are targeted at kids, more normally, it turns out, look downwards, which will meet a small child's eye line when they're walking around the supermarket. Cornell University's Anur Tal is one of the researchers behind the work and is with us now. Hello to you.
Hi, Chris.
Tell us, first of all, why did you decide to look at this?
Well, growing up, I feel personally I had a sort of connection that I felt to Captain Crunch in particular, and maybe that's part of me wanted to know why that might be. And also, we noticed just going around grocery stores that a lot of the times the cereals that are targeted towards children are looking down. So that made us wondering, could it be that in addition to looking down at something on the package, they're also looking down at people crossing the aisle?
So how did you then begin to explore how many packets were doing this and whether this was a general phenomenon, and also what impact it has on potential purchasers?
So we visited 10 grocery stores in Connecticut and New York states, and we looked at about 65 cereals, 45 of those targeted towards children and 20 not particularly targeted towards children. And then we analyzed the level of inflection of the eyes on these cereal boxes. So these are all cereals that had spokes characters. And what we found was that for cereals that were targeted towards children, the angle of the pupils in the eye was directed downwards on average at a level of about 9.6 degrees downwards. And that means that if you were a couple of feet into the aisle where children would be crossing, that a lot of these cereals are designed so that they're creating eye contact with kids. Now, we're not saying that this is a deliberate strategy. It might be completely incidental, because if you look at the packages, a lot of the times what these characters are doing are actually looking at their bowls of cereal. But it also happens that because of the angle they're looking at, they might be creating eye contact with kids crossing the aisle.
And how do you know, or how did you investigate what impact that line of sight might have on a potential purchaser?
So to follow that research up that looked at the angles and how the angles are different between adults and kids cereals, we ran a lab study where we gave half of our participants a picture of Trix cereal that has a rabbit on it that creates eye contact with them. We used just Photoshop to move the pupils around. And the other half of the participants saw a box of cereal where the pupils weren't directed at them. And we found that for people who were exposed to the cereal creating eye contact, they said that they felt more trust towards the brand, that they felt more connected to the brand. And also when given a choice between that and a competing brand, Fruity Pebbles, which is similar cereal in flavor, they chose it more. So 61% of the eye contact participants chose it versus 48% of the no eye contact participants.
Now, obviously, we don't know whether manufacturers have already stumbled upon this, and that's why they're using it, so we can't speculate on that. But obviously what you could do is to use your finding for good, because one could argue we could start using the same strategy on more healthy options to encourage more young purchasers to influence their parents even to buy healthier foods in future.
Exactly. So as I said, it might be that eye contact is incidental, but now that we know what it does, we can use that to promote healthier choices. So a lot of the healthier cereals that are, say, whole grain or don't have as much sugar aren't specifically targeted towards kids. But if we start featuring spokes characters on those that similarly create eye contact, maybe we'll promote more positive feelings in children towards those cereals. And then maybe a child crossing the aisle would say, hey, I want that high-fiber bran cereal versus the sugary Captain Crunch or Fruity Pebbles.
Well, we can live in hope, can't we? Anna Tal, thank you very much. What are you going to have on your breakfast cereal, Kat?
Well, I have porridge every morning, which is terribly boring. But I think the box I have has a nice Quaker on the front looking directly at me. That's why I like him. But if you'd like to follow up on the stories we've been discussing, there are references and transcripts for those news items on our website. That's nakedscientist.com/news.
You're listening to The Naked Scientists with Kat Arney and also with me, Chris Smith. And on to our main topic for this week now. Now, we've all been experiencing that frustrating feeling in the past where your phone or laptop battery is running out just at the wrong moment. But how actually do batteries work? And how do we build better ones? That's what we're going to be finding out this week. And to kick us off, we've got with us Fiona Strobridge, who's from Cambridge University, and also Graham Verity from GP Batteries. So let's kick off with you, Fiona. First of all, what actually is a battery? How does it work?
So a battery is an electrochemical device. So it converts chemical energy into the more useful electrical energy. And it does this via oxidation and reduction reactions, which involve the loss and gain of electrons, respectively, which then go around the external circuit to then produce electricity. The three main components to make this happen, you need to have two electrodes, the cathode, the anode, and you need an electrolyte, which is ionically conductive so that the ion or the charged species can be transported.
So when I look at a battery, which I might pick up in the supermarket or take out of my alarm clock, if I were to open one up, what would I see inside?
One of the classic examples to look at is one that's used in most laptops, phones, tablets at the moment, developed by Sony in 1990. It uses graphite as the anode. So it's got
carbon, like a pencil
carbon,
lead,
exactly, which has the sheets of carbon, which the lithium get intercalated or inserted in between these sheets of carbon. On the cathode, you've got a material called lithium cobalt oxide, which has a similar layered structure to graphite, but instead of carbon, it's cobalt dioxide. And then the lithium is in between these sheets.
How does that make the power, though?
So then the cobalt is in a 3+ charge state, and then it can go to the +4. Then the lithium ion then goes across the electrolyte and goes into the graphite, whilst the electron goes around the external circuit. Then they recombine, and that's how you get your electricity.
Oh, right. And so once all the lithium has made that journey, that's when the energy is spent from the battery.
that was in the discharge state. So that was actually charging the battery. And then to use it, the reverse process happens. So this is a rechargeable battery. So the lithium ions can then rock back and forth, because now the cobalt 4 plus could go to the cobalt 3 plus state. Then the lithium goes from the intercalated graphite sheets, goes across the electrolyte into the cobalt dioxide layers. The electron goes around the external circuit. So it was called the rocking chair battery because the lithium rocks back and forth. And you can think of it like a Victoria sponge with the 2 layers of cake as the sheets of carbon dioxide with the jam of lithium inside.
I love the analogy. I wouldn't like to eat a battery, though. There's lots of very toxic things in there.
Yeah, I wouldn't advise it.
Should we build one?
Yeah, so what we make in the lab is called a coin cell battery or a button battery, which is used in a lot of watches, phones, clocks.
There's a little thing. They look a bit like a coin, don't they?
Yeah, exactly. Really? So you've got the stainless steel base. And Chris, you can have a go at making one.
It's basically a little saucer, isn't it?
As well, exactly.
Yep.
So just to prove how easy it is. And then we've got our cathode material, which is lithium cobalt oxide, which we have as just a piece of paper today.
That would sit inside the base, just against the base.
Exactly. But then you need to have this rubber gasket sat inside the base because you can't have an electrical contact between the anode and the cathode, or else it'd be a short circuit.
Just short circuit inside the battery, wouldn't it? Yeah.
Exactly. And so then we have
so
our...
I've got my gasket. So I've basically got a little cup, like a stainless steel cup, and I've got my chemical in the bottom that's the lithium cobalt oxide that's going to be one source of the charge. Then I've put a rubber disc in there to separate it. Then what do I put in next?
Because the electrolyte is a liquid electrolyte, we need to have a physical barrier between the anode and the cathode. It's a glass fibre that sits on top of the cathode, and then you would soak it in electrolyte, and then we can place our anode on top, and then we need a stainless steel current collector and to ensure that we have a good electrical contact between our anode and our cathode.
Okay, and that's another little sort of disc that goes on top of the sandwich.
Exactly.
Yep.
And then the top of our battery, which is kind of like another saucer, like the base.
It just plugs inside.
This coin cell battery, you can think of it as a AA battery or AAA by just rolling your sheets of anode, cathode and electrolyte and then placing it in a cylindrical case.
There you go, Kat. Now you know how the batteries you're using work.
I do get through a lot of batteries, so let's bring in Graham at this point. Now, Fiona's explained how batteries work, but I want to do a bit of myth busting.
Okay.
So, and also a little, I guess, battery hygiene. So, for example, say I get a new phone with a nice new battery in it. What should I do to get the best out of it? Should I just plug it in straight away, charge it right up? How should I treat my batteries?
Well, the battery from the factory is probably delivered with something like a 30% charge. So you're probably going to want to charge it anyway. In actual fact, with a mobile phone, you're talking about something with a single 3.6 nominal voltage cell. And there is no need to charge it. So this is something that you're doing just so that you get a full battery. If you had more than one cell in there, then particularly moving away from lithium-ion batteries, so they're nickel metal hydride rechargeable batteries, and that's in a battery pack, you would definitely want to charge the pack to bring all of the cells into full balance. So you're starting with a well-balanced cell. Because if you were to discharge a battery pack, a nickel metal hydride battery pack, then one of those cells probably isn't going to carry as much charge as the others, and that's going to go into a low state of charge before the others, and will be driven lower than it should be by the others.
And so tell me a bit about how should we charge batteries. For example, I like to leave my phone charging overnight. Is that a good thing to do? It'll obviously be charged up quite quickly, but then I just leave it. Is that bad?
Again, here we're talking specifically about a phone battery, and that today is inevitably going to be lithium ion or lithium polymer. And the charger is going to have to look after that battery. If it were to go into overcharge, that becomes dangerous. And so the charger is designed to it's a constant current charge. The voltage will increase until it gets to 4.2 volt. And then the charger is going to do one of two things. It's either going to clamp the voltage at 4.2, and you'll see a diminishing current going into the battery to give it the full charge. Or in fact, at that point, it's about 70% charge and the charger is going to cut. If you were to continue to charge the battery beyond its capability, then you start to plate out metallic lithium in the cell. And that's when it becomes inherently dangerous. And that's what, we get the horror stories of lithium.
Okay, so best not do that.
So the charger is looking after it, and the charger is going to terminate the charge. So Yes, it's nice to unplug the thing because you think you're not using energy. In actual fact, chargers today will pretty well shut down and you're okay.
And we've had a question from Sybil Chobane who says, is there a difference between charging from the mains and charging, for example, from a USB? She says her phone seems to run down faster from USB. Is there actually a difference?
There isn't a difference. I mean, the USB probably doesn't, in some circumstances, have the ability to give quite as much power to the charge. But generally speaking, the USBs that you have on your computer will charge in roughly the same time.
And so for example, why is it that, if you have a phone for a while, towards the end of the life of your phone, the battery just doesn't seem to hold as much charge anymore? You have to charge it longer for less and less
the battery's
joy.
getting tired, isn't it? And that's
What's going on there?
That's what's happening with a battery. When we talk to designers, it's very important to realize that a battery is not like any other electronic component. It doesn't do exactly what it says on the tin, and you have to look after it, and your impurities are building up within the cell. It's becoming not as effective, and it's inevitable. A battery will not go to the end of its life and then just die. It will slowly fade away.
You're listening to The Naked Scientists with Kat Arney and also with me, Chris Smith, and you're on RN. In just a moment, we'll be hearing about how you can use MOS to power a radio. We're going to try and tune into our own programme just using the power of MOS. Chris Howe and Paolo Bombelli are here from the Biochemistry Department at Cambridge University with an amazing array, it's fair to say, of MOS all wired up in the studio. I wonder how it's going to go. So we've heard how we can use batteries best, but scientists are always trying to build even better batteries. And when I was in Chicago recently, I met up with a group at Argonne National Laboratory who are spending $100 million over the next 5 years to make batteries that they say should be, if they earn their money, 5 times better than the present generation. George Crabtree and Jeff Chamberlain are leading the project.
We need new batteries for the transformation of 2 of the most important energy sectors, transportation and the electricity grid. Transportation is obvious. It's to electric cars, replace gasoline engines. In the case of the grid, it's to enable renewable wind and solar energy to be deployed at a high level, say 20 or 30%. These are variable sources, and you need a backup for them.
Jeff, what's wrong with the batteries we have at the moment to fulfil both of those tasks that George has outlined?
So the batteries we have at the moment, lithium-ion, are the best batteries out there for transportation and actually for the grid. However, we need batteries that are significantly smaller, lighter, less expensive, recyclable, using earth-abundant materials. So we need to advance the technology, not just beyond where we are today with lithium-ion, but even if you go as far as you can go with lithium-ion, it won't meet the challenges that George just outlined.
Pretty high aspirations. Can you achieve this?
We're looking to be transformative. And less than, say, 5 times the performance at 1/5 the cost will not be transformative. The second answer is that it's well within what science will allow. So if you take the back of an envelope and a pencil and ask, what's the best I could do? It's a factor of 10. And technology in the energy sector typically delivers half of the theoretical potential. And that's true of lithium-ion batteries, for example.
So what approach are you taking, Jeff, to try to explore how to build these better batteries?
It's a materials challenge, developing new active materials down to the nano or meso scale, as well as the engineering challenge of how to put those materials into a chemical system that functions as a battery. So our approach is to couple those 2 approaches in a highly interactive way so that while the science is occurring to discover and develop new materials, we're actually putting them in cells and connecting ourselves directly with industrial partners to try to expedite that entire innovation timeline.
So George, how do you go about developing a new battery? Is it literally loads of wet chemistry, you're fiddling around with chemicals in the laboratory and seeing if they work together, or is there a strong theoretical arm to this?
So the typical way the R&D community operates now is, I would like to have a better cathode. Give me one, I'll try it. If it works, I'll use it. If it doesn't work, I'll throw it away and try something else. But they will not ask the question, why did it fail, or why did it work? And that's the question that we want to ask. So we're very different from typical battery R&D in this sense. We'd like to understand the phenomena and the materials of energy storage at the atomic and molecular level. And we feel that once we have that fundamental basic understanding, we'll be able to design rather than discover by chance but actually design the materials and the phenomena that we want in our next generation battery.
It's quite interesting that you're taking that fundamental we want to understand approach and then asking how do we use that to inform the development rather than just going hell for leather saying I need a better battery, let's just try lots of things.
Well, and the typical community today actually does everything by serendipity. I found something that works, I'm finished. We want to take that to the next level. And our feeling is that, as we were saying earlier, the beyond lithium-ion space is rich with opportunities. So once you understand why phenomena work and how the materials operate, you can then design more than one solution to the battery challenge. There may be 2 or 3 solutions that are equally, let's say, appealing, but for various different applications.
But returning to the question, which was how are you actually going about it, to what extent is it theoretical and driven on a computer, and to what extent are you actually getting your hands dirty with different mixtures of chemicals?
So on the very basic side of the spectrum of research that's performed in the center, we do combine computation and experiment. We've created, actually launched in a beta test format inside the center, something we call the electrolyte genome. And the idea is to take a somewhat genomic approach to developing a new chapter in the book of knowledge, if you want to think of it that way, on how electrolytes function. And we do that using supercomputers at Lawrence Berkeley National Lab and here at Argonne National Laboratory. So in a sense, we can explore, with our deep understanding of the quantum chemistry, we can explore new molecules computationally. We couple that with experiments done all the way from vacuum phase, truly looking at individual molecules on a single crystal of metal, all the way to putting it inside of cells and monitoring its performance and testing real time the degradation or the function of those materials as we build them. So the idea here is, again, to combine that deep science with the engineering, but coupling that in a very hard way with a new way to compute and look for, in a database, new discovery of new materials rather than a more hunt and peck method of developing materials in the lab.
That must save an enormous amount of effort because you can try things in the computer, which if they're going to draw a blank there, saves you then having to go and discover that by making the system in the real world.
That's the whole idea, that we'll save an enormous amount of effort by using the computer to look at thousands or tens of thousands of things that might take decades to do experimentally.
George Crabtree and Jeff Chamberlain, they're both from Argonne National Laboratory. With us is Fiona Strobridge from Cambridge University, who works out there sometimes. You got thrown out of your lab there by someone quite famous.
Yeah, I had a week of experiments at Argonne National Lab using the advanced photon source, and I got an email 3 days before my experiment time saying that I was going to have to vacate my lab because Barack Obama needed to use it for...
He was doing some experiments, was he?
Well, I think that's what he wanted to do, but, you know, he didn't quite have time. For the inconvenience, I managed to shake his hand.
There you go, Kat. Something you haven't done. You haven't met Barack Obama yet.
No, I certainly haven't. But who I do have here is Graham in the studio. And what I want to ask you about is rechargeable batteries. Now, when I was a kid, some time ago, my dad was very into rechargeable batteries, and we sort of used to put them in our Walkman, and they would basically last a tape's length and then just die. I understand now rechargeable batteries are a lot better. What's changed, and should people be using them, at home, your sort of AA batteries?
Yes, I believe it's time we looked again at rechargeable batteries. I know a lot of people had a lot of disappointing experiences years ago, but the technology has moved on. I mean, we never consider using a rechargeable battery in our mobile phones. So why do we do it in everything? Why do we not do it in everything else? This country alone spends £250 million a year on single-shot batteries, which are thrown away.
I think most of that's me, actually.
Yeah.
I buy a lot of batteries.
I mean, if I were to sell you a car and say it's going to cost you £80 to fill it up with fuel, but every time you fill up again, it's going to cost you 50p for the next 300 fills, you'd think that's crazy. Why wouldn't I do that? And yet with batteries, we don't.
And is it just the chemistry of the batteries that's changed that enables them to be better?
The chemistry has moved on. It started with NiCad. It's now nickel metal hydride. And yes, it's very, very different today from what it was 10, 15 years ago.
Cheers. Thank you.
You're listening to The Naked Scientists with Kat Arney and also with me, Chris Smith. Our quiz this week, don't forget, we want you to tell us what is the voltage on an AA battery, and it's a slight tricky question because there are two answers. This week we're talking about how to build better batteries, and while the team at Argonne in Chicago are looking at replacements for the lithium-ion type that we typically use at the moment, Claire Gray at the University of Cambridge is investigating how we can improve on the technology we already have. Kate Lamble went to meet her.
Well, I should first of all qualify, we're looking at a diversity of different approaches, of which one of them is lithium. And I think the reason why it's lithium is that lithium is the lightest element, it's one of the most reactive elements, and so that in principle gives you the highest voltage from the material. There's also a massive industry associated with lithium, and so it's quite important to actually work on the technology we have and improve what we've got. And why am I doing it? So if you take the material that's in your laptop, most of the laptops contain this material, lithium cobalt oxide. And it turns out that you can only pull out 50% of the lithium out of lithium cobalt oxide before two things happen. First of all, if you pull all of the lithiums out, you get structural rearrangements. And so what happens is the layers slip over each other, and then it becomes very difficult to put those lithium back in again. And so that means that you actually have to keep some of the lithiums in the structure. You can't pull them all out. And so we're carrying around 50% of dead weight in this lithium cobalt oxide that we can't use. And so if we can figure out how we can make other layered materials cycle, so charge and discharge, pulling out all of the lithium, we would have a battery that would almost be twice as effective. So that's reason number one. Reason number two is that lithium cobalt oxide, when you pull all the lithiums out, forms all cobalt 4+. Cobalt 4+ is not a very stable oxidation state, and it tends to lose oxygen. And so it's this loss of oxygen very rapidly associated also with heating and self-discharging that results in these safety incidents and the fires that you may have seen on the web. And so for safety reasons, again, we only pull out 50% of the lithium. So you've got this idea of the fact that you've got a factor of 2 just sitting in the materials we use today. And if we could get that to work, that's the difference between the Nissan Leaf, which has a range of 100 kilometers, going twice as far.
If you're sticking with lithium, because that's what we've got, that's the business model that we've got laid out, what other aspects of a battery could you possibly change to improve its performance?
Well, just going back to this idea of improving the electrodes themselves, so we talked about lithium cobalt oxide. So there are materials out there where people replace the cobalt with nickel and manganese, and those, instead of having 140 milliamperes per gram of charge, so that's just how many electrons can you get per unit of weight, they can allow you to cycle up to 200 and 220 milliamperes per gram. So that's a significant improvement. Then on the anode side, if you could find materials that stored more lithium on the anode, that would help. And one of the materials, for example, that we're looking at is silicon. So silicon allows you to store 10 times more lithium per amount of weight. And so that's very exciting. At the same time, going back to the cathode, you can increase the capacity, but you can also go up in voltage to increase the overall energy density. Now, the trade-off with that is safety. The higher voltage, the more oxidizing things become and increased risks there. But people are looking at trying to coat electromaterials and protect them in the same way that you might, if you think about a metal in the environment, you have a passivating coating on the copper on a church and similar things. We're trying to coat the materials to protect them from these very harsh oxidizing environments.
You've just mentioned a lot of different options. How do you go about testing the effectiveness of all the different options? Do you have to build each battery? And how do you decide which materials to test out first?
So there's been a lot of work using theoretical methodologies. You can take a structure now at this point and you can use first principle methods to actually calculate the voltage of the material. The challenge is actually to calculate the difficulty of pulling the lithiums out of the structure, because the lithium's got to move through different holes, and as they jump from site to site, there might be large activation barriers associated with that. In other words, you've got to supply additional energy to get it out. And we would supply that additional energy in a battery in the form of what's known as an overpotential, so a little bit of extra voltage to kick it out, and that's inefficient for your battery. So those are some of the challenges associated with using computations. So what we would do as chemists, there are people who go into the lab and make new materials. So one of the things that we're going for is, instead of just taking cobalt 3+ to 4+, we want to try and find elements where we can change the oxidation state by more than 1. So we could take nickel 2+ to nickel 4+. And at the same time, we need to be able to pull the lithiums out. So if we're going to go 2+ to 4+, we need 2 lithiums. So we can go into the lab with those sort of design criteria and try and make materials that might fit that.
What are the limits on how much you're able to improve these batteries?
So I think one thing that's important to remember is that if you have a material, it's made up of atoms and ions, and there are only a certain number of electrons that you can pull out per ion that you have in your material. And so if you have nickel, the chances are you're only going to be able to oxidize it between 2+ and 4+. And so the point is, for a unit mass of material, there are only so many numbers of electrons, and that puts a fundamental limit of where we're going to go. And so we can play games and we can find lighter materials, we can use a wider range of oxidation state, but there's a fundamental limit to what we're going to be able to do. And I think people do need to recognize that in terms of how we move forward in terms of developing strategies for electrification or for designing of new devices.
Kate Lamble talking to Claire Gray from the University of Cambridge about her work.
Now, we're always hearing about green energy, but how about a way to make electricity from plants rather than metals and chemicals? Well, that's the approach of Paolo Bombelli and Chris Howe. They're from the Biochemistry Department at the University of Cambridge, and they have built a MOS-powered, well, you've got both a clock and a radio in the studio. Hello to both of you.
Hello.
So, Chris, why on earth have you done this?
Well, because it seemed like an interesting challenge, really. We're in my lab, we're interested in studying photosynthesis, and you can think of photosynthesis as using tiny little electric circuits inside plant and algal cells, which are powered by the sun. And so you ought to be able to tap into that and get a small amount of electricity out. So it's like a kind of photovoltaic cell, but using plants or algae instead of silicon.
Paolo, how does it work?
Well, okay, first of all, believing or not, we got this little garden in the studio. And if anyone wants to see it, I would suggest to go in YouTube and look for MOS FM. Thanks to Fiona, we got an idea how a battery is made. And in some very similar way, this system operates, in the sense that we got an anode made by carbon and a cathode made by carbon again, but with nanoparticle of platinum that act as a catalyst. The photosynthetic organism, MOS, is harnessing the energy of the light and use it for something that is called water photolysis. That means breaking water in oxygen, and we all enjoy the oxygen, and also protons and electrons. Electrons can travel across the external circuit, and protons that are positive charges travel through the internal path.
So just looking at this, we've got lots of little pots of moss growing, all with crocodile clips attached to things coming out of the pots. That presumably is attached to the electrodes on which the moss is growing. So that's collecting the current from each of the moss cells, if you like. And how do you store or collect the energy, Chris?
So we can do different things. We can use it directly, and so we can, for example, use it to power a little digital clock if we want to, or an environment sensor.
Well, what's the voltage of a MOS, for want of a better phrase? How much potential difference does it produce?
Between 400 and 500 millivolts. And this depends on the redox potential of the system that donate electrons on the anodic side and the potential of the cathodic side. Something that has been discussed through this program.
400 millivolts, that's pretty good. That's half a volt.
It's pretty good. It's pretty good. As a matter of fact, this small garden is made by 10 pots. And overall, we go around 4 volts.
Super.
Because they are all connected in series.
But it does mean you're not going to get electrocuted when you're out in the garden spiking the lawn. So don't worry.
Can we have a go with it?
Oh yeah, definitely. I think we can try to power a radio.
Okay.
So
it'd be fun if we can tune into our own program.
Okay, I think everything is connected.
Well, that's an improvement on this program. Sounds much better.
I think we've doubled the listening figures.
Well, it's certainly working. There's a little red light on, and there is some static coming out of the speaker, but I don't think the content is quite up to scratch. Is it?
No, definitely not. Can I suggest perhaps, perhaps
just turn it down very slightly so we can hear what you're going to say. Normally, you would be picking up a radio. You're saying.
Yes, we do. Yeah.
So we'll put it down to there being some kind of shielding. There's a lot of metal around here, so it could be blocking the signals. But that's actually working. That's producing quite a lot of noise.
Yeah, at least it's noise.
And Chris, this is a demonstration, but could we use this more broadly to actually do useful things and power useful gadgets in the environment using this technology?
I think in the right kind of setting, then you might be able to exploit this. So particularly we're interested in situations where there isn't a good power supply. So you might be thinking of rural areas where in Africa maybe, or possibly refugee camps. Lots of possibilities where just a small amount of power can make a big difference.
Just moss, or will any plant do this?
Lots of plants will do it. This is just moss off the bike shed roof in the biochemistry department. So nothing fancy about it.
Thank you very much, Paolo Bombelli and also Chris Howe from the biochemistry department at Cambridge University. With what is that, the world's first moss-powered radio? Probably is, isn't it?
I think it probably is.
I think it's
somebody
correct,
out there will probably correct us.
Yeah.
If you know different, let us know.
You're listening to The Naked Scientists with Chris Smith and me, Kat Arney. To close this week's show, Hannah Critchlow's been getting her head round computers.
This week, we crunch into some data.
What I was wondering is, if the human genome contains 750 megabytes of storage, then why does my PC operating system need 1 gigabyte?
Does a computer need more data storage than human DNA? Surely our processing power is greater. To get to grips with the answer, Dr. Nick Goldman from the Wellcome Trust Genome Campus in Cambridge.
The genome makes a machine which is brilliant at learning, and then all your rest of your life experiences distilled into your brain are how you do all the things you actually do. So partly the reason why a genome can be small compared to the amazing complexity of the final product, which let's say is an adult, is because DNA and the genome is a brilliantly clever way of storing the instructions to make a fantastic machine. The baby can't do very much, but it has an unbelievable capacity to learn. But that's not in your genome. All those experiences you have are not in the genome. The system for storing them and making sense of them, it's in the brain. The brain is a machine, and the blueprint for that machine is the genome.
Clever us with our human genome coding for our clever brains, which contain a whopping 100 billion nerve cells, with new connections forming between these nerve cells as we learn new things. OK, so with that one figured out, what exactly is a computer's operating system? What does this do, and how does it compare to our genome?
Your average computer doesn't contain in it the instructions for making a computer. They don't ship you a blueprint for the machine. They give you a basic set of software, an operating system, that tells it how to do the most fundamental tasks. So it's not the blueprint of the body, which would be the genome analogy. It's the instructions of how to do certain tasks, not how to make the machine.
Thanks, Nick. And on Facebook, Pekka Alinka and Tony Spencer agree. Also adding that the DNA code has had about 3.6 billion years to evolve to efficiently store information for the blueprint of life. And the first type of processing unit or brain was thought to have evolved around 400 million years ago in arthropods. And in fact, Dr. Nick Goldman has recently used genetic code of DNA as a storage method for data. And it was super efficient, much more so than the current binary system used for storing data on computers. Well, with that one mulled over, we wonder what we can do with our machines to help further science. Listener M. Green got in touch.
Can I donate my living body to research?
So, once dead, you can donate your brain and body to science. But what about getting involved in research whilst you're still alive? Is this possible?
I wasn't sure if that was an offer or a question. If you can help us out, then you can email chris@thenakedscientist.com. You can also find us on Facebook, facebook.com/thenakedscientist, or you can get in touch @nakedscientist on Twitter. We better tell you the answer to the quiz. We asked you, what is the voltage of an AA battery? And it's a slight trick question. Fiona Stabridge is here from the University of Cambridge. She's a batteryologist. What's the answer, Fiona?
Well, it is indeed a very difficult question because obviously it depends on the chemistry of the battery. So the NiCad battery has a voltage of 1.2 volts, whereas the primary battery is 1.5.
NiCads being the rechargeables, the
Yes.
other ones being the throwaway variety.
Exactly.
Fiona, thank you very much. That's it for this week. Thank you to our guests, who are Madhu Sudan, Simone Di Giovanni, Marcus Pembry, Fiona Starbridge, Graham Verity, Paolo Bombelli and Chris Howe. And thank you to Kat Arney for joining me. The Naked Scientist comes to you from Cambridge University. It's supported by the Wellcome Trust, the STFC and the EPSRC. We're doing a Q&A show next week. All of your science questions answered, so just send them in to chris@thenakedscientist.com. I'm Chris Smith. We'll see you at the same time next week. Thanks for joining us. Goodbye.